Here's the question: is it possible medically to turn back the clock on the effects of aging? I see many of you giving me these authoritative, resounding answers. Now we're getting some enthusiasm, and I agree with you. There are certain things that we can do to help reverse the effects of aging, wear and tear on our bodies. And we're going to talk about one of them. It's something that in the scientific research literature they simply call hemorheology. And because we're at a scholarly venue speaking for continuing education, I've put up a couple of definitions from medical textbooks. The science of the physical properties of blood flow in the circulatory system. If that's not scholarly enough, how about this one? The science of the relation of pressures, flow, volumes, and resistances in blood vessels. Some people still say, well, what is it talking about? Hemorheology, if you just look at the word, I think most of us here know that hemo refers to blood. But what does rheology refer to? Do any of you know what rheology refers to? Occasionally in an audience, for a secular audience, there'll be a civil engineer. And they'll say, oh, we had to study rheology as it relates to waste streams. Rheology actually refers to science dealing with the flow properties, especially of complex substances. And blood is actually a very complex substance, right? There's cellular elements, there's proteins, there's, of course, water. Quite complex. Hemorheology is the science of what? If you want to make it simple, blood fluidity. That's what we'll be speaking about. In fact, hemorheology could be thought of as the science of the red blood cell. What is it that allows the red blood cell to flow smoothly throughout your body? So you say, okay, make it practical. Help us visualize what we're talking about. If we're talking about these red blood cells. Some years ago, we were invited to give a series of lectures in the country of Italy. Actually, one of the people that was involved in that invitation is sitting here with us, Dr. Roby Ann Sherman, who for many years, where is Roby Ann? There she is, Dr. Sherman. It's been good to see you again. We had a chance to visit a little bit this morning. Do you still do some work in Italy? Okay, I figured with all you're doing here, your hands were full enough. But so we were there, and they were working in northern Italy, she and her late husband, Bill, and others there in the Waldensian area. We were invited to speak in other places throughout the country, working with our church there in Italy. And during our time there, we rented one of those small Italian cars. And on one of our drives, we were driving in an old village, and as we were driving this vehicle, I don't want to extol my powers of depth perception that much, but I could tell as I was driving that one of two things was going to happen as I kept driving on that ancient road. Either we were going to spread the buildings apart with the vehicle, or the car was going to be damaged. How many of you, using the powers of deductive reasoning, could conclude what the likely outcome would be? That's right, the car would be damaged. And so, not wanting to have a rental car damaged, well, it was my name on it, I decided I would back straight up. No room for a 3-point turn or even a 20-point turn. All you could do is drive straight back. Now, the question is, the very basic question is, why couldn't I drive that car down that ancient Italian road? What was the problem? That's right, the car was too wide, it was wider than the width of the road. Simple, right? Now, here's the question for you as we speak about hemorheology and blood flow. How much clearance does a red blood cell have as it goes through the tiniest blood vessels in your body, the capillaries? So let me ask it this way. The width of the red blood cell, what percentage smaller than the width of the smallest capillary is it? Now, before you answer the question, being an experienced college teacher over the years, I learned that there was one type of question that would help my students learn the material better than any other. What kind of question do you think it was? I called it the trick question. okay? Now, I didn't believe in trick questions on examinations, but trick questions when I'm lecturing. So I just asked you a trick question. How much clearance, what percentage difference is there between the width of the red blood cell and the width of the smallest capillary? Would anyone like to answer the trick question now that I've primed the mental pump for a correct answer, hopefully? That's right. The red blood cell width is wider than the width of the capillary. In fact, over double the width of the capillary, smallest ones. So how can it travel through the smallest capillaries? That's right, it's got to squeeze through, it's got to fold over on itself. And the technical name for the shape of the red blood cell is a biconcave disc. I know you were looking at the picture and saying, oh, good to see those biconcave discs. That's what they are. It allows the red blood cell to fold over on itself, squeeze through the capillaries. Think about it just for a minute as we're trying to understand this concept of blood fluidity. What would happen if the membrane, the structure, the framework of the red blood cell was stiff or more rigid? What would happen? Yeah, it would impair the ability of the red blood cell to traverse the capillaries. How about if the red blood cells stack up together? No deal. They're not going to fold over if they're stacked up together. So there's a number of factors that it can affect blood fluidity. You say, okay, sounds interesting enough, but why are we learning about this? It's supposed to be practical lectures that have a bearing on heart health. Why is hemorheology important? Well, long before Wildwood even existed. And did I catch it right? 83 years that Wildwood has been around? Well, congratulations to all of you who are part of the team here at Wildwood. That's amazing. 83 years. But this statement far antedates Wildwood. In fact, it was part of the vision that is responsible for this institution to exist. It's a statement that you can find in a number of places, including the testimonies. Perfect health requires a perfect circulation. You may have seen it written as perfect health depends on perfect circulation. Sound familiar to any of you? You say, oh, sounds like, well, you wouldn't say this, but some people might say it sounds like beautiful poetry. But this is cutting-edge medical science. This is articulating in a few short words the science of blood fluidity, the science of hemorheology. So, I've given talks on hemorheology in many settings, and I learned something. For those of you that are health professionals, there's going to be no problem walking out the door, and you've probably heard of hemorheology before, and if you haven't, you'll be able to call your colleagues and say, oh, I heard a talk on hemorheology. But if you don't have a lot of medical background, you may walk out of a presentation, like many of my participants over the years, and you might be very excited about what we're going to talk about. We're going to talk about practical things that can improve your blood fluidity, things you can share with your patients, things you can share with your communities, with your churches. So you may leave excited, but if you don't have some medical background, you're liable to walk out and share your enthusiasm, maybe call someone on the phone, and you say, I just heard an amazing lecture about this topic, and someone said, well, what was it about? What was the topic called? You say, well, you can see that'd be a problem, right? So in working with lay people, we said, why don't we just call it the Methuselah factor? Now, why would we do that? How many of you have seen any blood work on Methuselah? By the way, who was Methuselah anyway? Yeah, he was the longest lived person on planet Earth. You read about him in Genesis. Remember, 969 years. We don't have any blood work. We don't have any advanced diagnostics that have been recorded for Methuselah, but I can guarantee you, since he lived 969 years, he had excellent what? Hemorheology. Some of you are catching on. For this presentation, if you're in doubt about an answer, there's a good chance the answer will be hemorheology or the Methuselah factor, okay? So hemorheology, We call it the Methuselah factor. And let's talk about some of the things the literature shows us improve as you improve your blood fluidity. You lower your risk of a number of problems, and especially relevant to this conference are the first two, stroke and coronary artery disease. If you want to lower your risk of these conditions, you want to improve what? Your hemorheology. Yes, that was a question, and the answer was hemorheology. Blindness. We'll talk about some of these, go into a little bit of detail. Glaucoma and macular degeneration. For those of you clinicians here, what is the leading cause of blindness among adults in the United States? Diabetes, yes, exactly. But if you don't lose your vision from diabetes and you lose it from something else, there's a good chance it will be glaucoma or macular degeneration. And both of them are closely linked to blood fluidity. Cancer was on that list. We might talk a little bit about that. Cognitive decline. If you want to maintain your mental faculties, you want to keep your blood fluidity optimal. We'll talk later in this series about high blood pressure, and one of the things that is a determinant of blood pressure is blood fluidity. Think about it this way, just to give you an illustration of something, and we'll go into more detail with some of the other topics, but think about it this way. What would make it so that your heart would have to generate more pressure to circulate your blood? If the blood's thicker, right? Cause and effect. So if your blood is not as viscous, if it doesn't flow, it doesn't have as low a viscosity, it doesn't flow as smoothly, then the heart is going to have to generate more pressure, and your blood pressure will tend to be elevated. It's more complicated than that, but just kind of giving you a window on some of this. Diabetes and its complications can be decreased by improving blood fluidity. Less likelihood of weight gain, better likelihood of trimming down if you can improve your hemorheology. Even arthritis and physical performance have been linked to blood fluidity. Research in young athletes. Improve hemorheology, improve muscle strength. Improve hemo. How many of you feel like you have such great performance, it wouldn't hurt you to slow down a little bit? You're a step ahead of everyone else. No, all of us could benefit from these things, right? So we're talking about something that is really powerful. Now, there are some challenges. If you say, you know what, I had a long trip here to Wildwood, and I'm kind of zoning out. You know, I'll just close my eyes and sleep, because I can just do a quick medical literature search of hemorheology, and I'll find everything DeRosa is speaking about. Well, unfortunately, a lot of the studies that look at this subject don't even use the word hemorheology, but they talk about some of the determinants of blood fluidity, and so we'll try to sort through some of that for you. And as we do that, let's take a few examples. Let's start with stroke. And this is not a new science. People have been studying this for years. Some of you know, I even wrote a book on the topic, and just for frame of reference, that book is dedicated to someone who is an inspiration for me on a campus, on a medical campus that was doing cutting-edge things decades ago. Would any of you like to guess what medical campus it was? Loma Linda, excellent guess. This person was on faculty at Loma Linda for a period of time, but I did not meet him at Loma Linda. Yes, I met him at Wildwood. Yeah. His name was Dr. Burnell Baldwin. Okay, some of you remember Dr. Burnell? And so the book is actually dedicated to him. And the reason I mention that is this is not like something that people have just started looking at. There's been data out there. There's whole societies that are devoted to hemorheology, whole medical journals that are devoted to the topic. And here's one of them. This is from a journal called Clinical Hemorheology and Microcirculation, over a couple decades ago now. And what they were doing is looking at determinants of blood fluidity, and they were looking to see if it had a bearing on the risk of what we call cerebrovascular disease. So either having a stroke or a transient ischemic attack. And I know this is especially designed for professionals. I know some of you are not professionals, so I'll try to speak to both audiences. I'm not trying to insult those of you that are clinicians. But so TIA, many of you realize, that looks just like a stroke, but it's fully reversible. Usually in a matter of seconds or minutes, but by definition, within 24 hours. And so all of these individuals, the 297, they have circulatory problems, blood flow problems to the brain, and they're going to compare them with healthy controls. What the researchers found, if they looked at a variety of determinants of blood fluidity, the worse these measures were, the greater the risk of stroke or TIA. Let's just talk a little bit about these. So hematocrit. Who would like to help us with a definition? What is hematocrit? Yeah, most of us know what it is. We say, well, how do you actually define it? It's the percentage of your blood that is made up of red blood cells. Okay? So if you go to your doctor and he says or she says your hematocrit is 45, what does that mean? 45% of your blood is made up of red blood cells. Okay? Now, here's the question for you. What if you could choose high hematocrit or low hematocrit, which should you choose? Yeah, you know I like trick questions. That's exactly right. The correct answer is neither. Okay? Too low a hematocrit, what do we call that? Anemia. That's not good. You need hemoglobin to carry oxygen, okay? For physical, for mental performance. But what if your hematocrit is really high? Well, let me just tell you a story. Maybe some of you can relate to this. There was a sport that was preoccupied with raising hematocrit. Even athletes engaging in illegal practices, blood doping to raise their hematocrit. Do any of you know what sport I'm referring to? Yes, elite cycling. And if you look into the annals of cycling, before there were agents that we have today, there's powerful agents we have that we can give by injection. Things like erythropoietin and other things that can actually stimulate your marrow to make more red blood cells. In the old days, you had to find a medical provider who would be complicit with you and allow you to have autologous transfusions. These athletes would go maybe a couple months before the race into some doctor's office, sneak in the back door. He'd take a pint of blood out, mix it with the appropriate preservatives, put it in the refrigerator, and then a month later, after your body had a chance to build up its blood supplies, you were back in the doctor's office. Why? Well, if you caught my timeline, it was 2 months before the race where you first showed up. Now you're back a month later. He's taking another unit of blood. Again, same process, and into the refrigerator. You got 2 units of blood now waiting for you. And the day before the race, the night before, where do you show up? At that doctor's office, and what does he do? Into your circulation, 2 units of your own blood. Now, why would a cyclist do this? You can carry more oxygen. That can help you perform better, but there's a price that you're paying. What is worsening? What do you think is worsening when your hematocrit goes up? That's right, hemorheology. You got the answer. That's right. Hemorheology is worsening. And so what then happened? It's staggering. You look at the data, I mean, as many as perhaps 24 elite athletes died either during races or immediately after. Presumably, they got a bit dehydrated during the competition. They were already challenged a bit with poorer hemorheology, and that tipped the balance. They end up with a stroke or a heart attack and died. So high hematocrit, a risk factor for stroke in this study. What about plasma viscosity? Now, someone left a bottle of water here. Are these like real legitimate plants, or are these, they look real. They look like the plants that I keep because some of them are dying. So I'm going to just do something. They can be watered? Okay. By the way, I like that look, actually. You know, it makes me feel at home. So what I'm going to do here is I'm going to take this bottle of water. I want you to watch very carefully. And I want you to observe what's happening. Can any of you see that? What did you see happen? Water flowing perfectly, pouring freely and quickly. How about if I had this filled with, let's say, honey? and someone told me that the reason that plant was looking a little sad is it needed some more honey. And would the honey have poured out as quickly? Why not? What's one of the differences? Viscosity. Okay? Does water have high or low viscosity? Low viscosity. The lower the viscosity, the lower the risk of stroke in this research. Plasma fibrinogen. Many of the clinicians know that fibrinogen is a clotting protein. Higher fibrinogen levels, poorer blood fluidity. And then we already talked about this in my illustration from Italy. If the red blood cells tend to clump together, what's going to happen to the blood fluidity? It's going to suffer, right? So when they looked at this, all of these things were predictors of stroke or TIA. You say, but how significant were they? Well, actually, let me answer it with another study. We're speaking especially about coronary artery disease, about heart health, and so I want to give you some data from a prospective study that looked at the connection between blood fluidity and heart attack risk. This is a European study that looked at some of these same determinants. You can see the first two sets of bars looking at fibrinogen and viscosity, and the second set of bars looking at white blood cell count. So what they did is they took the population and they divided it into what we call quintiles. It's like taking a pie and dividing it into 5 pieces. So if you're comparing the lowest quintile with the highest quintile, you're looking at the lowest 20%, comparing it with the highest 20%, you're looking at a sizable percentage of the population. You're studying 40% of the population. You following along with me? So you're not looking at the middle 60%, but you're looking at those with the best fibrinogens, that means lowest, and those with the worst fibrinogens, the highest. And as they followed these folks over time, did it increase their risk of having a major heart event much? Did it increase it much? It's in the range of a 4-fold increase. I mean, this is huge. Many risk factors. I mean, you'll hear a study. This study just came out. I was just reading a study. I won't tell you what it's about so we don't divert our interest. And they were talking about this increased risk of 10 to 20% increased risk in heart attacks. Is that significant? Well, it is significant. I mean, it was statistically significant in the study. And you know, if we have thousands of people dying from heart disease, right? So a 10 or 20% increase, that's a lot. But this is 4-fold. This is huge magnitudes of risk, okay? Viscosity, even more so.